So now we're going to look at power functions, and you might be asking yourself, what the heck is a power function? Well, you're really familiar already with things that look like y equals 2x squared plus 3x plus 8, and all of the methods we would use to graph or evaluate this function. But a power function really is just the part where I take the first monomial or the defining monomial. By defining, I mean if this is a second degree polynomial, then I take the squared term. If it was a cubic polynomial, then I would take the cubic term. So in this case, y equals 2x squared is the power function. Another example, y equals 3x cubed plus 2x minus 4 would be a cubic function, but if I take only the first power defining monomial out of it, I get y equals 3x cubed, and that's a power function. So written in its general form, I would say a power function, I don't need to write it again, is of the form y equals a, where a is our coefficient, x, our variable, raised to some power. Okay, so you have two examples here, but when we're dealing with a power function, we take into consideration all the possible forms or variations of n. So n can be an integer, meaning it could be to a 0 power, which sort of eliminates its value, but still, n could be negative, n could be positive. Well, actually, that would be negative or positive, which is what we care about off of the integers. Or it could also be a rational number, which is written with the fatty Q. So a rational number where you have an integer over an integer. All right, so let's look at some of the variations and how they would graph or evaluate. Well, let's talk first about what I alluded to just a moment ago when I choose 0 as the power. This would give me y equals ax to the 0 power, which we know is just a times 1, which is just a. And notice that by having 0 power, I've actually eliminated the variable and I've taken away its power or its powerness. So let's firm up our definition to say that the power function is a function written of the form y equals ax to the n, where n is specifically not a 0. So these other values are good. I can have a negative integer, a positive integer, and I can have a rational. But we want it to be a non-zero constant real number. So that was the first example, which eliminates one of our values or one of our ideas in the beginning of what a power function is. So our second example, let's choose our next easiest way of looking at this and say y equals ax to the positive integer. So we could say squared, we could say y equals ax cubed, y equals ax to the 4th, I'm going to write one more, y equals ax to the 5th, and on and on and on. Well, it turns out that when we eliminate these other terms from a quadratic or a cubic or from a polynomial, when we reduce the power function, or when we take only the defining monomial, the power defining monomial, these all behave all the way to infinity. They all behave very similarly. Positive integer powers behave similarly depending on whether the power is even or odd. So this is an even power, and 4 is obviously an even power as well. And so it turns out that y equals ax to the fourth is going to behave exactly, well, not exactly, but very much the same way that y equals ax squared is going to behave. So let's look at that behavior. Y equals ax squared, we know, is a parabola. And if I let a be, let's say y equals just x squared, so I'm going to take away a leading coefficient that squeezes or stretches, I get a parabola with end behavior going off toward infinity. So the limit as x values approach infinity of y equals positive infinity, and the limit as x approaches negative infinity of y approaches positive infinity as well. Turns out for the power function y equals ax to the fourth behaves very similarly. It's going to change a little bit how it acts here at the origin. It's going to stretch out a little bit, kind of take a little bit of a different shape, but it's still going to have exactly the same end behavior and exactly the same sort of root behavior as a quadratic. So we're used to thinking of a cubic function as having the ability to do something like this, where we have 3 roots. That's true, but once I reduce it to the monomial, it's not going to have all these loop-de-loos in there. So same thing's true with a square function, that you have a parabolic shape, and the y equals ax to the fourth is no longer a parabola, but it still has the same rough shape and behavior as a parabola. And then just like parabolas, if a is negative, so for example, if I have y equals negative x squared, this tells me to take the parabola and flip it over the x-axis. So I'm going to just flip it down. And then my change is that my limit as x values approach positive infinity of this function, now my limit is going to, or my end behavior is negative infinity. It's going to reach toward negative infinity. And so my limit as x values approach negative infinity y of the function y, it also approaches negative infinity for end behavior. Same thing with a power of 4, same thing with a power of 6, a power of 8. Any even power is going to have similar behavior, or the behavior you would expect from a quadratic, only the shape is going to be slightly different because of the power. So what about here, where I have to y equals ax to a fifth power function? Well, this is an odd power, an odd exponent, so it's going to behave in the same way that any even exponent is going to have a graph that behaves very similar to a quadratic. Any odd powered exponent power function is going to behave very similarly to the odd cubic function. So if I were to graph y equals x cubed, which we've all seen before, the odd function is going to behave in a very similar manner. The only difference is the shape of it will be slightly different. So the end behaviors are going to be the same. It's going to kind of flatten out here at the middle, and then the end behavior will do the same thing. So they're both reaching in the same direction as the simplest odd power, which is a cubic function, but the shape of the graph is slightly different. So in this case, we're looking at the limit as x values approach infinity of y as x values approach positive infinity, the function approaches positive infinity, but with a cubic function, the limit as x values approach negative infinity, so as you go this direction with your x values, the whole function is going to approach negative infinity. So your end behavior is to go to negative infinity on the left and positive infinity on the right. Exactly the same thing is going to happen with ax to the fifth, ax to the seventh, ax to the ninth, any odd powered function. And also duplicating exactly the same behavior we would expect if I wanted to graph, or if I had y equals negative x cubed, then I would just get the flip. So instead of going off to negative infinity on the left, it's going to go off to positive infinity on the left, and then it's going to do the same thing on the right by flipping over the x-axis. I mean, do the same thing, have the same flip over the x-axis. And so now my limits are, limit as x values approach infinity of y. Now my y values, my output is approaching negative infinity on the right, and then the limit as x values approach negative infinity, meaning on the left, I'm approaching positive infinity. So those are all the variations that you can expect to see in a power function that has a positive integer exponent. All right, so now let's explore what happens if I'm given a negative integer exponent. So this would be a case, so let's say example number 3, see if that's enough room to work in. If I have y equals ax to the minus 2 as an example. Well, what do we know about exponents and variables? This is really the same thing as a times x squared, or the same thing if I had y equals ax to the minus 3. This is really the same thing as a over x cubed. This is looking very much like a parent graph, right? This will have a similar shape to y, or f of x equals 1 over x. And we know that the parent form of this function, of the rational function, is to look like that, where y equals 0 and x equals 0 are both asymptotes. So we're going to get those sorts of shapes out of this sort of a graph. But something to pay attention to. Remember up here we started talking about whether powers were even or odd. And so we're going to do the same thing with these, because power functions are not specifically rational functions when it comes to parent graphing, or graphing using a parent. And so let's look at the behavior of the odd first. So negative 3 is odd, right? 3 is odd, I could say here. Whether it's negative or positive, it's still an odd number. And in our parent form, x to the first power is what we're really graphing in our parent exponential, or excuse me, our parent rational number. But the power on the x in our parent is an odd 1, the number 1. So the graph of y equals a to the minus 3 is really going to behave very much like y equals a to the minus 1, or more specifically, a over x cubed is going to behave very much like a over x to the first power. And so you're going to have your limit notation, you're going to have asymptotes at y equals 0 and x equals 0, and you're going to have limits that mimic the behavior on the rational function. So you're going to have the limit as x values approach positive infinity on the x-axis of your function is going to be 0, right? Because you're getting closer and closer and closer and closer to 0. I misspoke. 0. I didn't misspeak. And the limit as x values approach negative infinity of your function. So what is your function approaching at negative infinity? It's approaching 0 as well. But what do we think will happen if we have an even power? So in this case, I'm dealing with an even number as a power. Well, what do even numbers usually do? They make they make negatives turn into positives, because they make opposites out of numbers. And that's exactly what's going to happen here. It's going to turn this odd function into an even function. And what do even functions do? They reflect over the line y equals, or x equals 0. They reflect over the y-axis. So an even power is going to behave in the same way as the the rational function, except it's going to turn it from an odd function, symmetrical to the origin, and make it an even function, symmetrical to the y-axis. The asymptotes haven't changed, and the limits haven't changed. The in behavior is still the limit as x values approach negative infinity of the function equals 0. It gets closer and closer to 0, and the limit as x values approach positive infinity of the function also approaches 0. It approaches the asymptote on the y-axis. But where it differs is at the discontinuity or the asymptote, right? So what happens at the discontinuity? Well, the discontinuity happens at x equals 0, right? This is where it's discontinuous. And we evaluate it by looking at its intervals of increase and decrease. So in this case, in the odd case, if I started at negative infinity to see what's happening, notice that the function is constantly decreasing. Values on the y-axis get smaller and smaller and smaller and head off toward negative infinity. And on the other side of the asymptote, they come from positive infinity and head towards 0, which means they're constantly getting smaller. So this is continuously, or I should say, constantly decreasing. And I avoided using the word continuously because it is a discontinuous function. That's the only reason. It was a grappling between English and math language. And so let's look at what happens when we have a even power. Well, we've turned it into an even function, and so if I started at negative infinity, I can see that this function value gets constantly increasing, or is constantly increasing on the interval from negative infinity to 0, and then it's constantly decreasing, or constantly decreasing on the interval from 0 to positive infinity. All right, so let's look at our last, thank goodness last, right? Our last example, or our last situation. So we've eliminated that the power can never equal 0. We've looked at what happens when the power is even, or positive. We've looked at what happens when the power is negative. Now we want to look at what happens when we have a rational power. So that would be number 4, situation 4. So y equals ax to the 1/2. Well, what do we know about rational exponents? We know this is the same thing as a root x. And we know something about that already, because that's really just the parent function, f of x, equals the square root of x, and we know that that looks like this. All right. The other thing that could happen is, instead of having a equals x to the 1/2, I could have, oops, I'm getting ahead of myself. Let's look at denominator changes. So I have an even denominator, so y equals ax to the 1/3. Now I have an odd denominator. That's how we've evaluated all the others. So let's look at what happens with these in the same way. Well, this looks like the parent function, f of x equals the cubed root of x. And we know that the parent function for the cubed root is exactly the same as the square root, but we're not restricted from choosing negative x values, and so this one continues off this way. So we can say that the even and oddness of the denominator of this power impacts the shape of the graph in the ways we would expect, using all the other the same evaluations I've used on the other types. I'm not going to go over again the even odd changes. We've already done that. So if you wanted to know what would the general shape of, for example, y equals 2x, well, let's not put a leading coefficient because that always changes exactly the same way we're used to. Y equals x to the 1/5. you would know that that's the same as the fifth root of x, and that's going to behave very similar to the odd cubed root of x. But there is a new evaluation we have to look at whenever we have rational exponents, and that is that in Algebra 2 level work, we've always dealt with 1 in the numerator. So 1/2 would be the square root of x. But what happens if you have a number in the numerator? So say y equals x to the 3/2. What does that mean? Well, the 1/2 part stands true, so it's the square root, but the 3 means that we're going to raise the x to the 3rd power. So it's the square root of x cubed, and just for a property, and you may remember this from Algebra 2 because we did touch on it a little bit, you could write it this way, or you could write it with the cube outside. Either way, they're both exactly the same thing. So the question is, what does that do to the function? And it turns out that you end up with the same shape of a function as the square root function, except it rotates up a little bit, right? So these functions have this curve. See how that's the same or very similar to a square root function, but it's been tilted up? And it makes sense, really, because 3 would be the same, or x cubed in here, this would be like the cubic function, right? That would continue on this way. And so it makes sense that the shape would be some combination of a cubic and a root function. And because the cubic is bigger, that's going to have more power over it. But it is still a square root, so this side isn't going to exist. Okay, so whenever you have a rational exponent that doesn't have 1 in the numerator, you end up with a shape more like a parabola, but it's not a parabola. Then what happens? Question is, y equals x to the 2/3, say. In this case, we're looking at the cubed root of x squared, where the root is the more powerful part of the function, or the largest value. So the shape is going to take more of the cubic shape, but squaring it is going to make it even, make all of the input values positive, which means if I put in a negative x, I'm going to get a positive y instead of a negative y, and I'm going to get a shape more like this. Then you have the added complication of y equals x to the negative 3/2, which just turns out to be y equals y equals 1 over the square root of x cubed, which is kind of the same, but the inverse of the same. You can see how this form of graph starts to get more complicated. When you process these, you will do it by graphing points, by plotting points, and by using a graphing calculator, or having some sort of an input that helps you see these shapes more clearly. But whenever you're given a power function with a negative exponent, or with a positive exponent that's not 0, you will have to make most of the evaluations on the graph by comparing it to the parent you're familiar with, which is the x squared, the x cubed, the 1 over x. And then there'll be a little bit of familiarity work done with the root functions. But like I said, for the fourth kind, this is really just an introduction at PreCalc. Phew! So I know this has gone on for a while, but I do feel like we need an example, and since since this is the more difficult type of graphing, let's look at an example of one of these. So let's graph and evaluate f of x equals 2x to the 3/4. Okay, so this is really 2 times the 4th root of x cubed. So I know that my two choices for shape come from the 4th root, which would look a lot like the square root which would go like that, and the power, the cubed power, which would look a lot like the cubed function, the general cubed function, which would look like that. But notice that my 4 is bigger than my 3, which means that the root function shape is going to win out. So I'm going to have a shape like that. Okay, so we're not going to worry about this one. But we want to see what happens with all the rest of this gobbledygook to that shape. It's clear that there's no squeeze or stretch. Oh, there is a squeeze or stretch, sorry. It's clear that there's no translation on the X or Y axis because there's no plus something in here and no plus or minus something out here. So all I need to do is find out where this shape lives. Since there's no translation, I know that the origin is still the origin. And that makes total sense because if I put in 0 for X, I get a 0 inside. That's totally allowed with a radical. 0 times 2 is 0, so I still have my graph still starts at the origin. And then to find out the shape, how does all the rest of this stuff affect it? I'm just going to plug in a number. So I'm going to let f of x, or I'm going to let my x value equal 1, because 1, 1 is our favorite plotting point after 0. So if I put in a 1 for x, then I get the cubed root of 1, which equals 1 cubed, which equals 1. The fourth root of 1 is 1 times 2. I'm going to get a 2 out. And so now at 1 and 2, and remember, if you plot the point, you have to label it, then I'm going to get this shape. And as tough as these are to graph, that's actually not as tough as it could be.